periodically as you march through the elements, from atomic number 1 to atomic number 112. As you march through, properties start to repeat themselves. So if you line up the repeating elements in columns, you get a periodic table where all elements with similar properties are in columns. So all the elements in column 1, for instance, have a similar properties. And now we understand the quantum mechanical nature of that. Even though the periodic table was assembled in its current form hundreds of years ago, there's been a few tweaks where we've realized where the F block transition metals occur, but the overall structure has been fairly consistent for hundreds of years. But we understand now with the advent of quantum mechanics why these elements have similar properties. For instance, in column 1, all the elements have an S1 outer electronic configuration. It's either 1s1, 2s1, 3s1, 4s1, etc. down the periodic table. So from the outside, you're looking at a 1s electron all the time. And of course, that imparts similar reactive properties to those elements. And as you go across, s2, and then you start to fill p orbitals. And then you fill d orbitals and f orbitals. In fact, we know the periodic table is set up so that the s orbitals are filling here, the p orbitals filling here, d orbitals fill along the center, and f orbitals along the bottom. So quantum mechanics exactly predicts the structure of the periodic table, even though the periodic table was set up well before quantum mechanics was understood. Now, these periodic properties in the periodic table tend to go in trends as you go across the periodic table. And those trends are interesting to analyze. So let's look at a few. We've talked a little bit about ionization energy already. That's separating electrons from atoms. There's also electron affinity. So electron affinity is the addition of an electron to an atom or an ion. So either taking an electron off or forcing an electron in are the two reactions we can look at. So for ionization, that's removing an electron from a species. That energy is always positive. I always have to put energy in to remove an electron from an ion or an atom. And that's something you can take to the bank. If you take nothing else home from Chem 1, take home the fact that when I pull apart an electron from an atom which has a positively charged nucleus, that requires energy. And if it requires energy, we're going to call those positive energies in Chem 1. And if energy is released, we're going to call those negative energies. So here's an electron affinity reaction. Electron affinity is adding an electron to a species. Now you might think that atoms don't want to accept electrons. But it turns out that adding an electron often releases energy. That goes to a lower energy, more stable state. And that's because an electron free in space and an atom with a positive charge at its nucleus, the most stable state for that electron to be is near that positive charge in the atom. So adding an electron is usually a reaction that releases energy. It's more stable to have that electron. And that's an interesting property. In fact, you don't expect it to be the case. And there are a few elements where they're not too excited about taking that electron. And some, one or two, that you actually have to force it on. You have to put a tiny amount of energy in to make the ion. So let's look at these properties more carefully. Here's some elements on the periodic table. Sodium, potassium, rubidium, that's going down a column of the periodic table. And chlorine, bromine, iodine going down a column of the periodic table. So the trend as I go down the column is it's getting easier to ionize. The ionization energy is decreasing. And that's pretty easy to understand because what I'm doing is going to bigger and bigger atoms. Even though I've got more positive charge at the nucleus, I've got lots of electrons shielding, and I'm getting pretty far away when I go from S1 to S2 to S3 to S4 to the outside principal quantum levels of these atoms. So an electron far away and well shielded is a little easier to take off than an electron close by. And I see that in chlorine, bromine, and iodine as well on the other side of the periodic table. I have a decrease in ionization energy as I go down the column. For the electron affinities, there's the same general trend. That is, the electron affinity for sodium. Sodium releases quite a bit of energy when you make it into sodium minus. It likes to accept that electron. 53 kilojoules per mole are released, where rubidium, only 47 kilojoules are released. That makes a little sense too. Rubidium with its 37 electrons, the 38th one that you put on is a little less kept track of there. It's got going from 37 to 38. It's not as big as a perturbation as going from 11 to 12 electrons at sodium. But either way, both those elements are willing to accept an extra electron and even go to lower energy states when they're the minus ion as opposed to the free atom and a free electron. Same thing with chlorine, bromine, and iodine. We have a decrease in electron affinity as I go down the column on the periodic table.